Okay, so last lecture we are discussing about we discussed about the integration method for position of center of mass, and we had seen these couple of examples. So let's continue from that point onwards today. Okay, so we'll continue with the application of integration methods for calculation of center of mass. Okay, so the next example we will see in this regard is center of mass of a thin uniform hemispherical shell. Okay, so we have like a hemispherical bowl like this, which is open from here. But as mass section. So we can see here that this will become an axis of symmetry. So let's say the center of curvature lies here. And in fact, let's take the y-axis downwards. So y-axis is the symmetry axis, and O is the center of curvature. the open base in the YZ plane, sorry, in the XZ plane. So therefore, center of mass, it will lie on the y-axis. So let's say center of mass is somewhere here. So the position of the center of mass we will find by using this integration. And in this, once again, because it's a surface distribution, so dm will be like a sigma dA, where dA is some differential part of the surface of the hemisphere. Okay. So now, can you tell me what will be the convenient way to take dA? How I should slice the disk?
Sir, into rings.
Yes. Okay. So I should slice it using a plane which is parallel to the XZ plane, right? Or parallel to the base, and slice it into very thin rings. So each of those rings is a differential mass dm, and each of the rings has its own center of mass at its own center. Okay, so it's very easy to locate. So here we will take sigma, of course, as total mass upon 2 pi r square, because surface area of hemisphere. But dA, this we will take as the area of a thin differential ring sliced by a plane parallel to the XZ plane. So that geometry now looks like this. Okay, so consider a thin ring like this over here. So this is where the center of that ring is lying. Now see, the thing is that the ring's thickness, which is the differential quantity here. Okay, so the thickness of the ring is this thing here, say dl. So it's a very small thickness, but also that is actually a tiny arc. So if this angle is theta, then that thickness of the ring is subtending a very small angle, d theta. So the thickness becomes r d theta. And the radius of the ring, let's say small r, so this thin differential ring it has a thickness. First of all, it has a radius, small r equal to, you can see, capital R cos theta. Okay. And it has a thickness dl equal to r d theta. Okay. So once again, I'm showing the geometry in a sideways diagram so that it looks as if you're looking in the two-dimensional plane. So in this diagram, the ring that we have sliced, it will look like this. So you've taken this angle to be theta. So this radius here becomes r cos theta. Okay. And this thickness becomes r d theta like this. Okay. So the area of this ring will be circumference into thickness. So it can be expressed like this: 2 pi r square cos theta d theta. That is the area of the ring. And therefore the mass of the ring is a very simple term. It is. Now this ring's center of mass is at y equal to, in this diagram you can see this is y. So that y coordinate of that particular ring center of mass is r sine theta. So now we will substitute these things, y dm, and integrate this expression above. Okay. So I'll just minimize this and go through this for a moment. Okay.
Done, sir.
Okay, so let's take it from this point. So now we substitute these in the integration required. Now, can you tell me what should be the limits that we will take for the integration? You will substitute y with r sine theta. You will substitute dm with m cos theta d theta. But what should be the limits? Anyone? What limits of of theta we should take? Starting from
Minus
the
pi by 2 to plus pi by 2.
see, if we are taking a ring over here, we have taken this angle to be theta now. We are starting from which ring? The ring at the top, right?
Yes.
The ring at the top will have theta's value how much? 0 now.
Yes.
And the bottommost ring here, that will have theta's value how much?
Pi by 2.
Pi by 2. Okay. So it would have been minus pi by 2 to plus pi by 2 if it was the full sphere. Getting my point?
Yeah, so you'll have
Because
to
it's,
do only half and multiplied by 2, right?
so it's only half. So it is 0 to pi by 2. Got it now?
Yes.
Okay. So that is the limits. Okay. Now how we'll do this integration? Sine theta into cos theta integration. How we'll do? Couple of methods we have. One is we can write it as sine 2 theta by 2. Integration sine theta cos theta. It can be written as sine 2 theta whole thing divided by 2. Okay, so take the half outside and then use basic formula that antiderivative of sine theta is minus cos theta. So sine 2 theta's antiderivative will become how much? It will become minus cos 2 theta divided by 2. So this becomes minus cos 2 theta divided by 4 plus c. That's one method we can use. Okay. And then put the limits. Or another method we can use is the one I'm going to use here, that we can substitute sine theta as z. So cos theta d theta becomes dz. Okay. So the integration becomes z dz type of integration. So that's also a very convenient way of doing this. Okay. So r into now sine theta cos theta. Sine theta will write as z and cos theta d theta as dz. So when theta is equal to 0, z is becoming how much? It is sine 0. So it is 0. And at theta equal to pi by 2, z is becoming sine pi by 2. So that's 1. So it's r into integration z dz, which is z square by 2, but limits z going from 0 to 1. So interestingly, the position of the center of mass comes at r by 2. The hemispherical shell.
Sir, your screen isn't visible.
The screen is invisible, no? Just a second to reload it. Okay, so it should be back online now.
Yes, sir. So the y is equal to r sin theta we just directly got from the fact that the center of the ring would be at the
Yes.
center,
So
right?
basically that thin ring is a mass dm, and its own center of mass is where? At its own geometrical center.
Yes.
So we can think of that dm lying at which y coordinate? At the y coordinate, which is its own center, which is r sine theta from the origin above. You know?
Yes, sir.
Now, interestingly, apart from this, we can do one more thing. We can use this kind of integration method to prove that the surface area of a sphere is 4 pi r square, or surface area of a hemisphere is 2 pi r square. Okay. So that's one thing other than this that we can do using this integration. See here, we have got the area of the ring as this. Okay. So from this, we can see that the surface area, the formula we've already used above, okay, for sigma, but we can prove that formula. Surface area of the hemisphere, open hemisphere, that area should be equal to integration of dA for all the rings. So dA over here, see what it was? It was 2 pi r square cos theta d theta. But the limits will be from theta equal to 0 to theta equal to pi by 2. So this is a nice way to use calculus to demonstrate that area of a hemisphere is 2 pi r square, or therefore area of a sphere will become double of this, or 4 pi r square.
So if we were doing for a sphere, then for every theta, there would be two such rings which would satisfy.
Yes, yes. Or you can just change the limits and make it from minus pi by 2 to plus pi by 2.
Oh, okay.
Either way, just double it or make it minus pi by 2 to plus pi by 2. So this type of integration application, it is called a surface integration. So we are using definite integration to find the surface area of a certain body or of a certain structure. Okay. So this application of integration will be part of your class 12 math syllabus, where you learn to find out various surface areas, not just things like spheres, but also more complex surfaces like an ellipsoid, which you get by rotating an ellipse, which is like a potato-shaped kind of surface, or a paraboloid, the type of surface you'll get if you rotate a parabola, a y is equal to x square type of parabola. If you rotate it about its axis, then you get a different shaped bowl, not a hemispherical bowl, but a paraboloid bowl. So how to find the surface area of these, or even the use of volume integrations to find out volume of various different objects. Like you can prove that volume of a cone is 1 by 3 pi r square h, which I think we had done in the last lecture also. Okay, now let's move on to our final volume integration. I mean, volume distribution of mass. So in this series of standard derivations, okay, we have discussed about semi-ring, semi-disc, right? Then solid cone. Then today we did hollow hemispherical shell. Now the final example in this series of derivations we'll look at is the case of the center of mass of the solid hemisphere of uniform density. So the diagram looks exactly same, but the difference is now we have to imagine that it is a solid body, not a hollow shell. So once again, we will slice it using a plane which is parallel to the base. But when we slice it this time, what kind of shape we'll get for the differential element? We'll get a disc.
Solid cylinder.
We'll get a solid disc. Instead of a ring, we'll get a solid disc. So once again, the center of mass will be somewhere here. So center of mass is at some y coordinate. So this time when we are executing this integration, what is dm going to be? It is going to be density into volume, where density will be total mass divided by 2 by 3 pi r cube. Because solid sphere's volume is 4 by 3 pi r cube. So hemispheres is 2 by 3 pi r cube. So this is the density. Now the volume dV we should take for a differential disk, as we discussed. Now when we slice this into differential disks, the way we treat the geometry of the disk is going to be slightly different compared to how we'd seen the geometry of the ring on the surface. Because for the ring, we had considered the thickness as the differential arc r d theta. But for the ring, we will have to consider the thickness as the vertical thickness and not the thickness on the curved surface. We will not consider this thing as the thickness here. Rather, we will consider the thickness as this. Okay. So if this position is y, this position is y, then this thickness here, it is dy. Okay. And the radius of this ring is r. So this disk is r. And this radius is capital R. So we are considering a differential disk. It's a thin solid disk of radius small r and thickness dy. So volume of that disk will become this. Okay. And here r square is capital R square minus y square. So this is what we will substitute as the volume of the disk in the above integral to find the center of mass of the hemisphere. But in this case, solid hemisphere. Okay. So now try to execute the integration yourself. Calculate and tell me where should be the position of the center of mass. You have to just put this in the integration above. Okay, density also I've already showed you. So now you have to just execute the integration with the proper limits. Okay, so think carefully how we'll take the limits and work out the integration and tell me what will be the YCM for the solid hemisphere.
Got the answer, sir.
That, sir.
Done, sir.
So what is the value you are getting for center of mass's position?
Sir, 3r/8.
Yes, very good. Okay. So apart from that, you can also use this integration to prove that volume of hemisphere is 2 pi r square. That is something aside from this you can do. Volume of the solid hemisphere. That will be integration of dv for the disks. Okay. So that will become integration of pi r square dy from y equal to 0 to y equal to capital R. So that is so if you do this integration, you can show that it will be 2 by 3 pi r cube. And therefore solid sphere will just become double of this. So the standard formula 4 by 3 pi r cube, that also can be demonstrated from integration by either doubling this or changing the limits from minus r to plus r. Now coming back to center of mass. So what is the y coordinate of the center of mass of this disk? It is y itself over here. So therefore y coordinate of the center of mass of the hemisphere, that will become integration y dm divided by total mass. So integration y into rho into dv. So this dm, which is rho dv, will become 3m upon pi r cube, sorry, 2 pi r cube. Okay, that's your rho into dv, which we have written above as pi into r square minus y square dy. So that can be written as 3m upon 2 r cube into r square minus y square dy. So we're going to substitute this dm over here. So y into dm, dm is this. Same limits 0 to capital R. Okay, and final step, just substitute these limits and work this out. So it is at a distance of 3r by 8 from the base of the hemisphere. So that is the final conclusion for this.
Sir,
Yes.
Why exactly did we approximate the dy thickness as r sine theta in one, r cos theta in one case, and I mean, sorry, the r d theta in one case and dy in the other case? Like, it's the same shape that we are approximating, right, as a cylinder. So,
Sorry, come again. I didn't understand. Why did we?
so in the first case, we took the dl thickness as rd theta, and here we are taking the same like thickness part as dy.
Right,
So,
okay. Because see, the difference is there. It is a ring. So the ring is like, imagine it's a ribbon which is wrapped on the surface of the hemisphere. Na? So the thickness of the ribbon is in which part? It is in the spherical part. Na?
yes, sir.
So that is dl.
That is-
And when you slice the solid hemisphere into discs, okay, it's actually not exactly a disc because the side of the disc is a little bit curved. Okay. It's like this, no?
Yes, sir.
Okay. But remember, we are considering volume of the disc. So if we take this as the thickness, then it will become too much volume, no? Because it's like, if it's a disc like this with a little bit of extra part here, but that extra part is negligible. You understanding? No?
Okay. Huh.
So the thickness of the disc has to be taken as this vertical thickness because we are concerned with its volume and not with the area of the shaded part. Got it, no?
Yes, sir.
So that's why the volume of this will be considered as pi r square dy. But on the other hand, if we were considering the surface area, then we would consider this dl. Okay, the area of this would be considered as 2 pi r into dl instead of dy.
Got it. Thank you.
so the second last line, that would be y cube, right?
The second last,
R square y minus y cube.
y cube, correct. That's how we're getting y to the power 4 by 4, correct. Okay, so this integration is clear to everyone? Any doubt? Okay. So these are the standard derivations, okay, and formulae of center of mass of various types of rigid bodies. Okay, so now with this, we will move on to, again, more applications about linear momentum conservation and eventually about collisions. Okay, so let's now go back to a bit of recap of the concept of, if we have a system which has different masses in it, which are in motion, then the motion of the center of mass and the momentum of the system, etc., how they are described. And linear momentum of a system. So if we have a system that consists of different bodies or different masses, etc., which are moving about, then the center of mass of the system is also likely to be in motion. So we had seen that position of center of mass, because it's a discrete particle system, now I'm considering it like this. So it's given by the summation method. So accordingly, different displacement of center of mass also becomes summation of individual mass into displacement divided by summation of mass. So differentiating this relation gives us velocity of center of mass is summation mass into velocity divided by summation mass. So this formula also tells us about momentum of a system. Linear momentum of a system of particles, therefore, is described as total mass into velocity of center of mass. And that also becomes the summation of mv for all the constituent particles. Okay. So here m is total mass or summation mi. Okay. Now from this we had also seen that if we differentiate this relation, we get the impulse momentum theorem or the Newton's third law application, that net external force acting on a system equals to rate of change of momentum. It also shows that if the net external force on a system is zero, then its linear momentum is conserved. So the velocity of the center of mass should remain constant if this condition is satisfied. So this is the net external force. So if that is zero, then linear momentum is conserved. And then, of course, on the other hand, if linear momentum is not conserved, then the center of mass can also have an acceleration, which comes by differentiating this. So if you see, the numerator is the net external force acting on the system, because summation of MA is summation of all forces. So internal forces cancel off in action-reaction pairs. So the acceleration of the center of mass only depends on the net external force, which comes from summation of MA for all the particles. So now we will look at this type of situations, applications in more detail. Linear momentum conservation, this one. So the condition for linear momentum to be conserved is that the net external force is zero. So let's look at some examples of this. So let's try out this question. So we have this situation that on a frictionless floor or frictionless horizontal surface, if we have placed a wooden plank of certain mass and length, so this plank has a mass of 25 kilograms and its length is, let's say, 10 meters. Now there's a person standing at one end of the plank and his mass is, say, 50 kilograms. Okay. Initially, the system is at rest. Now, at t equal to 0, the person starts walking towards the other end at a uniform speed of, let us say, 20 centimeters per second relative to the plank. Make this question a bit easier by taking his mass to be 75 kg. Numerically, it will be easy. So he starts walking at a speed of 20 centimeters per second, but relative to the plank. So we have to find out the velocity of the center of mass of the plank plus person, the velocity of the plank and the velocity of the person, all these things in ground frame while he's walking. And when he reaches the other end, by that time, what is the displacement of the center of mass? Sorry, not the center of mass, but the displacement of the plank. So how much is the plank's displacement by the time the person has reached the other end of the plank? So what principle will we here apply to understand how the system is behaving? If you take the person plus the plank as a system, what can you say about the net external force when he starts walking? Is there any net external force? No, no, because the ground is frictionless. No. So because the ground is frictionless, okay, when he starts walking with his feet dragging against the plank, he's pushing the plank backwards with friction, right? And the plank is pushing him forward. So he develops a forward momentum, but the plank develops a backward momentum like a recoil. And because there's no friction on the ground, so the plank will slip backwards even as he's walking forwards. So that whole situation will be such that the center of mass, okay, of the system, what should happen to the center of mass? It should remain fixed, okay? It should not move. Because the net external force is zero. And initially the velocity of the center of mass was zero. Both were at rest. So VCM remains zero because there's no external force. Okay, so use this as a hint to try and work out, okay, both these things, the velocities, okay, as well as the displacement.
I sent you the answer. Is it right?
Okay, so let me verify the answers. Okay. I'll first take you through the process, then I'll give you the answers so you can verify. Couple of people have sent the correct answers. Okay. So what is happening is that this is the state of the system before he starts walking, that both the plank and the person are at rest. Okay. And we can see where the position of the center of mass is. Okay. Because even though not given, we'll have to assume that the plank is a uniform mass distribution. So its own center of mass is most likely at its geometrical center. That is at the midpoint of the plank, right? So before he starts walking, you have his own mass of 75 kg located, you can say, at one end of the plank. And the plank's own center is here, let's say. So you have mass M1 of 25 kg located here, and both are at rest. So where is the center of mass of the system? The center of mass of the system will be somewhere here, such that look at this distance. You can calculate it like this. This is where the center of mass is located. Velocity of center of mass is 0 right now. Is this clear to all of you, this concept here?
Yes.
Okay. Now what will happen is when he starts walking, let's say he has a forward velocity of v2. So the plank will start going back at v1. Okay. So because the velocity of the center of mass is 0 initially, okay, before he starts to walk, and the external force on the system is 0. Because if you see the force picture, what is happening is when he starts walking, he applies a backward frictional force and the plank applies a forward static friction. But the external force on the system is 0. So that means momentum of the system remains conserved. That means velocity of the center of mass remains 0. Throughout. So we have the formula then that PCM here will become minus M1 V1 because it's in the negative direction plus M2 V2, it's in the forward direction, divided by M1 plus M2, and this should be 0. So M1 V1 in the backward direction should be M2 V2 in the forward direction, so that the momentum of the system remains 0. Okay, so we have 3V1 is equal to V2 by substituting 75 kg and 25 kg, or we have V1 is to V2 is 1 is to 3. Now, what will be the relative velocity of the person with respect to the plank in terms of V1, V2? Can you tell me that? If the person is moving forward at V2 and the plank is going backwards at V1, what is the velocity of the man with respect to the plank? It is the velocity of the man in the ground frame minus the velocity of the plank, right?
Yes.
So this relative velocity will become plus of V2 minus of minus V1. No? Two things going in the opposite direction. So relative velocity becomes sum.
Yes.
Right? Okay, so this is V1 plus V2. And it is given that V1 plus V2 or the relative velocity is how much? 20 centimeters
per second.
That's 20 centimeters per second. Okay. So from this, we can see that their individual velocities are like this. V1 is 1/4 of V relative. So 1/4 of 20. So that is 5 centimeters per second. And V2 will be, oh, sorry. Just a minute. I made some mistake here. I substituted wrong. I think M1 is the mass of the plank. So it's 25. So this is the other way around. V1 is the velocity of the V1 is the velocity of the plank and not the person. This should be 3:1. So V1 will become 3/4 of the relative velocity. So V1 will become 3/4 of 20. And so the actual velocity of the person will only be 5 centimeters per second. The direction of the velocity is as indicated. The person is actually going forward. And the plank is actually moving backwards. So now same thing we'll do with displacement also. Okay. So you can see that velocity of center of mass is 0. That means displacement of center of mass will be 0. So that means that by the time the person reaches the other end, if he is displaced by S2 and the plank is displaced backwards by S1, then they should be related in such a way that the center of mass has not moved. So this is the center of the plank. This is where the center of mass of the system is. Okay. So by the time the person walks to the other end, so this is the actual displacement of the person in the ground plane, whereas the displacement of the plank is this. So that the center of mass will remain here only. Center of mass is not shifted. So again, you can see that displacement of the center of mass is 0 means that plus M2S2 minus M1S1 should be 0. So from here, and S1 plus S2 in the diagram, you can see is the length of the plank. It was 10 meters. So the displacement of the man will be plus 2.5 I cap in meters. Whereas during this time, the displacement of the plank will be backwards by 7.5 meters. So that the displacement of the center of mass will be 0. Okay, so this is like the typical application of conservation of linear momentum, conservation of position of center of mass in this case, because linear momentum itself is 0. So we will continue with these type of examples and get into collisions, which is the most important application of conservation of linear momentum in the following sessions coming up next week. So hope you have understood this, people. That's it for today's lecture. So have a nice day, all of you.
Thank you, sir.
Okay, sir.
Yes, and Merry Christmas.
Merry Christmas, sir.
Thank you, sir.
So please send this PDF.